Okay, we are doing the sequel of our lecture on property of limits. Uh, this is now the second part of that lecture, and this is also a part that I was doing live, but unfortunately there was lots of interruptions there, so I'm recording this separately to have this lecture done correctly. Okay, so what we were doing in the previous lecture was that I have these 11 properties that we listed, and they're all of the properties that are important. We are going to use those properties, and the one last property that we were doing was the property that we call a squeeze theorem or a sandwich theorem. And then I have this particular limit that I wanted to show you how it is that a limit of a sine x divided with x when x goes to 0 is equal 1. And that is, of course, related to this nice picture that we have. So that you can notice in this picture, so this is a random angle. The angle is positive, but if it's a negative angle, so it'll be just the other side going backwards, like clockwise, and it will be just a mirror image of this. So it doesn't matter whether the angle is positive or negative. We are looking for some angle that is going close to 0. Okay, so that's what we're trying to do. All right, so I'm gonna make this picture on the board. All right, again, you can just follow the lecture and add your own notes. You don't need to follow what I'm doing on the board. I mean, you don't have to write what I'm doing on the board. So I want to make a unit circle, so I'm not gonna make units, but the idea is that unit circle has a radius of 1, and so I'm taking a random angle. We can call this angle an x or a theta. I use the Greek letter theta for the angle because the x is kind of unusual that you usually call angles by Greek names, alpha, beta, and so on. So what I want to show is that limit when x goes to 0 of a sine x over x is equal 1. Now you can try to see that for yourself. Calculate for some really small x. You see what this is going to be. It's going to be close to 1, right? And as you approach to 0, something like 0.1, 0.01, 0.001, and so on, every time you calculate this expression for that particular x, you can use your calculator, you'll get something close to 1, which means that you suspect that the limit might be 1. Okay? Now, whether I'm going to call this x or, as in my picture, theta, it makes no difference, right? So I'm going to label that the same way as it's in the picture. Let's call it theta. So the theta is the thing that goes to 0. Okay? Now, in this picture, just in the lecture, I have a couple of triangles here that I want to make point of. This a large triangle, then I have this smaller isosceles triangle with two sides the same, both of them are 1 radius. And I also have a circular sector, this pizza slice. Okay? As you can notice in the picture, the big triangle has the biggest area. The smaller triangle has smaller area. And the pizza slice has the area that is in between. So it's bigger than the area of the pizza slice. I'll make it a little nicer here, so you can see. The area of the pizza slice is slightly more than this triangle, but it's also smaller than the bigger triangle. So now the question is, what is the area of each one of those triangles and a pizza slice? Well, the bigger triangle has the area of a half of a tangent of theta. And you can ask question, how do I know that? Because I know that because this thing has to be multiplied with this thing, so that would be this piece here times 1, which is just basically this guy, and then you have to divide by 2. That's how you calculate the area of the triangle. The only question is, what is this? And that's a tangent, because we know that the angle has a tangent equal to the opposite side shorter divided by the closer shorter side. So that would be this thing divided by this. So this must be tangent, because that's what the tangent is. Opposite divided with adjacent. Okay? And again, so tangent times 1 divided by 2 is the area of the bigger triangle. So that's the area of the bigger triangle. The smaller triangle, this piece here, this triangle, you can calculate again by using the area of a triangle, which would be the base times the height divided by 2. Now the base is 1, so what's the height? Well, the height is a sine of this angle. This is a right angle, so this height divided by the hypotenuse is the sine of the angle. And the hypotenuse, of course, is 1. So, of course, you know that this must be sine and this must be cosine, right? So, we have here cosine of theta divided by 2. So again, this is the area of the smaller triangle, this triangle here, this isosceles triangle. Okay? The bigger triangle has this area. So, now the question is, what is the pizza slice area? The pizza slice area is the area of a circular sector, and if you have studied properly pre-calculus in trigonometry, you learn that the area of the pizza slice is the length of this arc time the radius, which is 1, divided by 2. This is sort of a triangle. Base, which is the length of this arc, time the height, which is 1, divided by 2. But of course, this is actually theta in radians, because that's the whole idea in unit circle. The length of an arc is theta in radians. So the angle in radians basically means the length of the arc. So that's the story of trigonometry. What is the measure of radian? So basically, you have the area of the pizza slice is this guy. Okay. So again, the base theta times the height of the pizza slice, which is 1 radius, divided by 2. Okay, so now you have this. This is the relation of these three things, the two triangles and the pizza slice, or we call it circular sectors. I'm referring to pizza slice because you're probably very familiar what a pizza slice looks like. Okay, so now if you multiply this all with 2, you get rid of the halves. Nothing specially changes otherwise than that. You just don't have fractions anymore, and you have this thing here. Now the next thing excuse me, I made a mistake. This is sine theta, right? Not a cosine. I think I said sine, I just simply wrote cosine for some reason. Yeah, this is sine, and this is cosine. Cosine, sine, okay? So now what the next thing I want to do is to divide everything with the sine. So if I divide this guy with the sine, is 1. If I divide this guy with the sine, is this thing here. And if I divide this one with the sine, this is tangent is sine over cosine. So if you divide it with the sine, you get just reciprocal cosine. Okay. And now I need to flip this. So yeah, you can have a question. So what if the theta is equal to 0, then sine is equal to 0, so you have 0 over 0. How can you divide with 0? Well, I am not interested when theta is equal to 0. I'm interested when theta is coming close to 0, right? That's the story of the limit. We're not interested in what's happening at 0. We're interested in what's happening when theta is something really small, but close to 0, but not 0, okay? So this stuff here is now okay. Only thing I need to have this in reciprocal, right? This is sine of theta over theta. I have theta over sine of theta. So I can flip it up, flip it around. So I get this flip of 1 is 1, flip of this guy is this thing here, and flip of this guy is a cosine. Okay? What happens when you're flipping the fractions? The inequality changes this way. Right? So the idea is, 1/2 is more than 1/3. 1/2 is bigger than 1/3. But when you flip it, 2 is smaller than 3. So when you flip it, the inequality changes. But that's what we have. Now the question is, you have two functions. One of them is a constant one, another one is a cosine. And the question is, what is the limit of this guy here? The limit of 1 is when x goes to 0 is 1. As theta goes to 0, this guy is going nowhere. It stays 1. This is a constant, so we have this property number 1 that says the limit of a constant is 1. So this guy goes to 1. Okay? What happened with this guy when theta goes to 0? Well, that's an easy thing to know. I mean, take a look at the picture. What happens if angle becomes close to 0? What's a cosine? This is currently cosine here for this angle. Well, as you go lower, lower, and lower, the cosine becomes 1. There's nothing special that happened with the cosine. Now, of course, if I need to do a longer explanation, I'll try to make a nice picture, and you can see that, but I think you can think of yourself. This thing also goes to 1. Okay? So, we have a squeeze theorem now. Squeeze theorem says, if we have two functions, this is one function, this is another function, right? Y equal 1, y equal cosine of theta. And then this is a third function that is in between. And squeeze theorem says, if you have two functions that are sandwiching the third function, the squeezing third function in between, and both of these functions at the ends, the bordering functions, both of them are going to something that is the same. Now in this case 1. Then the middle one must go to the same. And that's the proof that this holds. So this is an important limit that you're going to have to remember. Right? So we didn't do that by algebra. We use geometry. And you can say, oh, I don't like this because you're doing the pictures and in your picture the angle is positive. What if angle is negative? Because this means when theta goes to 0, either positive or negative. Well, you think yourself. If the angle is negative, you're just going to make a picture on the instead of having this picture I was doing, you're going to make this picture I could do. And you're going to have the same. This is a negative. Right? Negative angle. You're just going clockwise from the positive part of x-axis. That's all there is to it. And you have a mirror image of what is above. So it's going to be the same thing. I mean, the limit is going to be the same thing. Because the area is going to still stay in the same relation. So you can write this over again and think for yourself, but you will have this whole again. Okay. Now I have a couple of examples here that are using this, which are important in the lecture. I have a couple of examples. So the first example, it says that can you find the limit of sine of 2x over 3x when x goes to 0, right? Now, I'm using the language of an angle here, so I might want to revert back to the function language. The language of function is usually, you don't call angles, you call x and y's, x independent and y dependent. It doesn't make any difference really how you're going to call that label. You can use any way you want it. But here I'm using the functional language, an algebra language with the x's. Okay, what is that? Okay, you like to talk about this one, but this is different. It's 2x on the top, not an x. On the bottom I have an x, here I have 3x. What can you do about it? Well, this, what you can do. You can easily convince yourself that this is correct. I'm just extracting a fraction 2/3 out. Because if you cancel 2 and 2 here, you end up with a 3 multiplies x. This is exactly what this is. So I'm doing nothing special. This is basic algebra. Why did I do that? Because I want to match this with this. Okay? So the next step is that this is a question. What is this going to when x goes to 0? When x goes to 0, 2x goes to 0. That's the property number 4, I believe. multiple if the function goes to something, then the multiple of that function goes to multiple of that something. So if x goes to 0, the 2x has to go to 2 times whatever x goes to, which is 2 times 0. So you get 0. So when x goes to 0, 2x goes to 0. Vice versa is also true. When 2x goes to 0, x must be going to 0, because x is just a half of 2x. So this and this is the same story. Okay, what is now that I have here? I have the constant multiple of something. Constant multiple, there is a property number 4. The 2/3 can go out. So I'm not going to write a whole new line for that. I can just simply write 2/3 in front of the limit. And now the next question is, what is the limit of this? Okay? Again, you can replace 2x with theta if you like, and you're going to have a question, limit of theta going to 0 of sine of theta divided by theta. And we know that's equal 1. I know you're going to get confused here, because here is x, here is 2x. But it doesn't make any difference, it's a label only. Okay, so you can call this theta. Theta is 2x. So theta goes to 0, sine of theta divided by theta. And we know that that must be 1. Because that doesn't matter, you call this theta or x or whatnot, this is general conclusion. So this is 1. In other words, you have the limit is 2/3. This guy is still around, right? 2 times 1 is 2/3. 2/3 times 1 is 2/3. I just said 2 times 1 is 2/3, not really. 2/3 times 1 is 2/3. Okay? So that's how this limit is done. You can also tons of limits like that could lead very simple result. And anytime you have a multiple here, you have multiple here, you can just think about it. I'm just extracting 2/3. Sort of, yeah. I'm not extracting anything. This is not extraction business, but the result is the same if you think that way. Okay? I have another limit for you. It's another example of the sort of the same, not the same. Limit of, let's change a little bit routine. X time sine of 1 over x. This is one of the functions I did some long time ago. I was actually showing you the picture of this function. And I wasn't really talking about limits, I was just talking at limits in general. So I wasn't really calculating anything. Is this limit possible to find? Okay, now the kick about this, that this is actually another application of a squeeze theorem. Okay, the squeeze theorem, I need to find the squeeze here. Here's going to be the squeeze. Sine of 1 over x is always between 1 and minus 1. Okay, it could be 1 or minus 1, but it's always between those two, because sine is always between 1 and minus 1. So it cannot go anywhere above that or below. It has to stay in this range. Now, if you multiply the thing with an x, you will get one times x is x. Okay? Now it's possible that x is negative. So if x is negative, this would switch and this would switch. And again, I'm not interested in what happens when x is equal to 0, because this is a limit, and limit is a story around, not at x equals 0. Okay? So again, so for positive x, this is what's going to happen. For negative x, you would have just a reverse. Okay? But in basically what I'm saying here, the positive one must be on the side of the biggest and the negative on the side of the smallest. Now, if x is negative, this is the positive absolute value of x. Okay? Negative of some negative number. So what I'm saying here is basically you can avoid all of this problem by just putting an absolute value here. And then you know that this is negative and this is positive, so the relation stays this way. So again, I put some kind of argument. The main point is that this is never outside of the negative 1 to 1, right? So therefore, x multiplied this will not cross the absolute value of the x, because take any number you like, the number is always no more than absolute value of itself, and it will not go below negative of its absolute value, right? Because number can never be lower or smaller than the negative value of its absolute value, right? So this will hold. Okay, now you have this sandwich. You have one function, you have another function, and you have a function in between. So that's a squeeze. All right, so the question is, where is this guy going to? If x goes to 0, the absolute value of x goes to 0. I think that's clear. You can spend some time arguing it, but that's just entirely obvious, I think. Right? You can make a picture and talk about epsilon delta situation, but if x goes to 0, the absolute value goes to 0. Now the same thing happened here. The only difference is the sign here. And the sign is not going to make any difference if you go to 0. You can go to 0 from either side. So which means that I have this guy goes to 0, this guy goes to 0. So therefore, by the squeeze theorem, this guy must be going to 0. That's the squeeze theorem says. If you have a sandwich, so the function in the sandwich is between two functions whose limits are the same, then the limit of the function in between must be also the same number. And that's what we have. That number is 0, right? So that's another example of a sandwich theorem. I said that this guy is important to remember. This guy is not so important to remember. It's just an example of squeeze theorem use. Okay. Now I have one more that is an important limit. One that we will use at least once, and maybe even more than once, in calculus down the road, and it's a very important limit, and that's the guy. And again, we are looking for x going to 0, because that's what when it's interesting, right? You can't really just plug it in, because you have to divide with 0. So what is this limit? All right, I can tell you right there from the get-go, this limit is equal to 0, but I have to show it to you. Of course, you can do that yourself. You can get the something really small, something close to 0, like a 0.1, a 0.01, and then calculate this expression. You'll find out that this actually is going to be close to 0. So then you can start to suspect maybe the limit is equal to 0. Okay, it is. Now here's the thing. You can multiply this with 1 plus cosine x, 1 plus cosine x, and that is obviously okay, because this is 1. You're not changing anything. Okay, just simply making the things bigger. You can say, why would I want to have that? Because I want to make a square here. Okay, I'm rationalizing something. Cosine is not really a radical, but I can do the same thing. So I have a minus b, a plus b. So this is the thing that you do when you rationalize something. So I'm not rationalizing something, but I'm multiplying that with 1. The only question that you can have, so what if this is equal to 0? Because then you're multiplying with something that could be undefined. Because if this is equal to 0, you're dividing 0 with 0, you don't have anything. And you're changing the whole thing into undefined thing. No, I'm not really interested in that. Cosine is equal to 0 only when the x is equal pi half, or minus pi half, or something like that. But it's far away from 0. I'm not really interested in going far away from 0. I'm interested in staying around 0. X goes to 0. So I don't care about that. Right? So I'm okay with this. Now I'm going to multiply. If you multiply the top, you're going to get the 1 minus cosine squared. Right? This is a minus b, a plus b. When you multiply, you get a squared minus b squared, square of 1 minus the square of cosine, which is what I wrote. Down there you have to do some more work. But really I'm doing nothing. I'm just simply writing multiplication. Denominator with denominator. Now I'm going to split this up. Okay, this guy is a sine square, right? Sine squared plus cosine squared is equal to 1, so if you subtract cosine squared from 1, you get sine squared. That makes a little bit simpler numerator. Okay, I'm just writing that so I don't have to write a whole new line for that. Now I'm going to split this. I'm going to use a product rule. Okay, first I need the sine of x over x, because I know what that is, right? This guy. And then I have some left over. I have another sine x, and 1 minus cosine x. Oh, plus, excuse me. So this time this is here, this time this is here, so I'm okay. Now I have to use a product rule. The product rule is going to be, one of the properties says that limit of products of two functions equal product of their limits, if you have limits. Of course I have limits of the first one, right here, that's 1. The only question is what is the limit of this guy? And the limit of this guy is equal to 0. How do I know that? Okay, here's how. When x gets close to 0, so I'm arguing here, there's some sort of intuition here. When x goes to 0, cosine goes to 1. I showed that on the picture before, right? Here you go. Here you got an angle, and this is the cosine, right? As this angle goes to 0 from either side, from positive or negative side, this thing goes to 1 in a unit circle, right? So the cosine goes to 1. If x goes to 0, the cosine goes to 1. The cosine goes to 1, 1 plus 1 goes to 2. I mean, 1 plus something that goes to 1 goes to 2. And sine of x goes to 0. Sine is a different story, right? Again, the picture of an angle. This is a sine, and if this angle goes to 0, then sine becomes 0. So you have 0 over 2, which is 0. So the limit of this guy is 1, the limit of this guy is 0, and the story is that the limit is 0 overall. The limit of this, the limit is equal to the limit of this, which is equal to the limit of this, and you can erase this, it's just 1, and then you have the limit of this. So we have a second limit here of importance. You always have to write this under limit where the x goes to. Sometimes people forget that, and then you think about what does he mean by limit without telling me where x goes to. So you have to be careful. Again, so these are two important limits, two important trigonometric limits. You will see down the road that many trigonometric limits could be reduced to this, and there are some properties we're going to use looking for limits that this guy is going to be important. So these are the two limits, two trigonometric limits that you have to remember. And then down the road I will always remind you. Do you remember this sine trigonometric limit we did a long time ago? Or do you remember that cosine trigonometric limit we did a long time ago? That's what I'm talking about. Okay? So we will recall them. They are important limits in our story. Okay? Now I want to do two proofs of the properties for you by using epsilon delta definition. And those properties are not trivial at all, even though they sound like something really simple. So I'm gonna do the the property constant multiple. The limit of a constant multiple of a function is equal to the constant multiple of a limit of a function. This is the property number 4. So it says this: limit. It says a lot more. It says like that: if limit of f of x when x goes to, I don't know, a is equal to something, let's call it del, then when c something different than 0, we don't want to have 0. When c 0, when c is not equal 0, limit of a c of f of x when x goes to a is equal c times l, which basically says this: the limit of a constant multiple of a function is equal to the constant multiple of limit of that function. We say that in a fast way is that a limit of a multiple is equal to a multiple of a limit, which is what it is. Okay? And I can say, why do I have this not equal 0? I will need that in my proof, but I don't really need that for the conclusion, because if C is equal 0, what happens here, if C is equal 0, what happens is that you have a 0 times something, which is always 0. So this stays 0 no matter what x is. And on the other side, you have a 0 times something, whatever that is, which is also 0. So the conclusion holds. The limit of a 0, when x goes to something, is 0. It's not going to be anything to prove here. So I really don't need the C to be different than 0. Okay? I will need that for my proof. So in every other case, I really need to actually prove that. Okay? So what we do know is that this is true. But that's assumption. We are making assumption that the limit of f exists, and that limit is actually L. Okay? So what we know is that this is whenever, this is an epsilon delta definition, whenever you choose any epsilon bigger than 0, there is delta bigger than 0, such that whenever x is no more than delta, this is the distance of x and a, that x is no more than delta away from a. This is the distance between x and a. So this says the distance between x and a is no more than delta. So whenever the x is within delta environment of the a is the target of x, then f of x is within epsilon distance of L, the limit. So whenever the x is within delta distance from a, the target of x, then dy, the f of x, is within epsilon distance away from the limit. That is so because the limit is going to be L. So this holds. This is the fact. Right? Because we are assuming this is true. Okay, now I have to show you that this is also true. So I have to use the same story with epsilon and delta. But I have to show it, because this is assumed to be true. So, let epsilon be anything. Something bigger than 0. Any number bigger than 0. Take another epsilon. Let's call it epsilon 1. My starting epsilon divided with c. Can I do that? Yeah, because I'm assuming that c is bigger than 0. So I did assume that c is not 0. I could use it smaller than 0, I could use bigger than 0. Let's assume that it's bigger than 0. If I use that it's smaller than 0, I'll have the same story, only I'll have a little bit trouble with the signs on the way. So I'm going to just assume that the c is bigger than 0. I already told you that when c is equal to 0, this is not really nothing to prove. If c is different than 0, there's something to prove. But I'm also not going to use the c is bigger than 0, just to make my life easier here. Because other than that, I need to use an absolute value of c. That's just going to make the whole story more complicated. But it's not going to make it any different. in terms of logic used. So what do we know now? We know that for this epsilon 1, this is going to hold. So not this epsilon, but for some epsilon 1, this guy, this must hold. There must be some delta. There is delta. So that whenever x minus a is less than delta, then I'm just reading this, f of x minus L must be less than epsilon 1. I'm using epsilon 1, not on this original epsilon here. I'm using epsilon 1 from this story here. It's just a label. If you like, you can call this epsilon 1. What does it make a difference? Nothing, right? But that's kind of like weird, because I had no reason to call it that way. But this time I'm using it. So it says whenever epsilon is bigger than 0, whatever epsilon you want. So in this particular case, I want this epsilon. Okay? So whenever you have that epsilon, I have this one here, there will be a delta, so that whenever the x is within delta distance of a, then f of x, so the y of that x, will be within epsilon 1 distance of L, the limit. Right? I'm just simply using this fact here. Okay, what does it make difference now if I multiply this with the c? So let's multiply then. What it follows, if you multiply both sides with c, is this. Okay? Now read it one more time. This is epsilon 1, so we multiply c times epsilon 1, you multiply this guy times c, which means you get just epsilon. Now use c to be positive. If c is positive, you can just go inside, because you have a positive number. You can try with any numbers you like. Absolute value of a number times a positive number is just going to be absolute value of that number times that positive number. So this guy go inside. So I'm getting c f of x minus c L. Okay? And you just need to focus on what are the important parts here. Let epsilon be bigger than 0. Any epsilon. This is arbitrary one. There is delta. So that whenever the x is in less than delta away distance from A, you have that c times f is within epsilon distance away from c times L. And that's the definition of limit. This is limit of this function, because whenever you choose an epsilon, you can find a delta. So whenever the x is within delta distance of a, you will have that this function of that x will be within epsilon distance away from CL. That has to happen if you have a limit, and we don't just have it, right? So this is assumed, and this what I circle is exactly what it has to happen if CL is the limit of this guy, and it is. It's exactly what it happened. Okay? This is an epsilon delta proof of the property number 4. Okay? You will have to really think about that. It takes time to understand this. I know. And this plays no role anymore, so I will now just erase it. And you look at this piece, what is on the board, and think about that. Okay? I'm going to prove one more property. That property that I want to prove is going to be the property of limit of a sum is equal to the sum of the limits. So I'm going to have, so I'm going to erase this now. You think about it. You can always stop the video, right, and just look at that and, go again what I was trying to tell you, and think about it. This stuff is not trivial at all. This is a serious mathematics. And in mathematics, we do serious proofs. We don't believe into anything until we are satisfied beyond reasonable doubt that the logic has been followed properly. Right? Pictures are not enough, our opinion are not enough. That's not how it works in any science, but definitely not in mathematics. Okay. So, okay. Now what we have is the property that says this. Limit when x goes to a, so this is the property number 5, limit of a sum is equal to the sum of the limit. So I have two functions. Let's call one f, and let's call another one g. And when you make a sum of these two functions, and you look for the limit, you're going to have the limit of the first function plus the limit of the second function. And obviously, provided that those limits exist. If those limits do not exist, then you don't have this. So, provided that there is a limit, limit of f of x when x goes to a, we'll call it L, and the limit of g of x, there is also something when x goes to a, and let's call it k. Okay? In which case we can just simply make a little changes here. So equation is always more readable if you write less of it. So I'm going to call this L, I'm going to call this guy k. It might not be in alphabetic order, so what should I do? K and L, right? K and L, let's go. K and L in alphabetic order. K and L. So K plus L. So what this property says, so I'm going to just underline. This is what we need to prove. Okay? It's not proven yet, unless you exhibit logical rationale of why this would hold. For some reason my camera went out of focus. Let me see if we can find it now. So basically I'm proving this property number 5. I'm switching the screen, so I'm hoping that I'm going to get this back in the focus. So this property number 5, limit of f plus g is when x goes to a equal to the limit of f, which is an L stated here, and plus limit plus k, which is the limit of g stated here. So I did it in reverse here anyway, alphabetic order, right? Okay. Now I'm back in focus. I don't know why did I get out of focus. Okay. Anyway, so I get this. I need to prove that. So let me go back. I'm gonna match the non-alphabetic order in the paper because I don't want you to get confused here. Might as well make any difference. You can call it any way you want. So the limit of f is L. The limit of g is k. Makes sense because you call usually the first function limit just L. Limit stands abbreviated for limit. And the second function now I don't have anything better, so I'm calling k. All right. So this holds. Now, what do we have here? We have this statement that whenever you have an epsilon, you will find a delta. Any small epsilon you want, you will find a delta. So whenever the x is within delta environment around A, the f of x will be within epsilon environment around L. So whenever the x is within delta environment around A, whenever the x is close to A, but in a particular way, epsilon environment, the delta environment, the f of x will be within the epsilon environment around L. And the same thing is going to happen here, but you might have another delta, like a delta 2. So I might have to write that. This is a fact because we are assuming it. Right? We're going to prove this provided this holds. So whenever epsilon is bigger than 0, there is delta, let's call it delta 1, bigger than 0, so that whenever x minus a is less than delta, then f of x minus L, the limit of f, is less than epsilon, delta 1. Okay, let's read this one more time. So, whenever you choose an epsilon, write this nicely. Whenever you choose any epsilon you like, positive one, there will be some positive delta. We're talking about the distance, right? So that whenever the x is less than delta 1 away from a, the y, the f, will be less than epsilon away from the L. And that holds because we assume that this is the limit of this function. So this is a fact 1 by assumption. The fact 2, the same story for G. So just the language is different. Whenever epsilon is bigger than 0, there is, let's call it delta 2. I'm not claiming it's the same delta. So I have to, this is arbitrarily chosen, but the delta depends on this guy. So I have to call it delta 2 because I don't know if it's equal to the first one. So that whenever x is less than alpha delta 1, delta 2, then g of x endless emails. I'm gonna have to shut them off. This happens. So these are two facts. All right. So what this says is the same story for this guy. So this is a fact because he said provided. So this is assumed. This is assumed. This is assumed. So we now have to prove that this is also true. So what I'm saying here is that whenever you choose delta epsilon bigger than 0, you'll find some delta, not necessarily equal to this one, but some delta, so that whenever the x is within the delta environment of A, the g of x, the y, but through g, will be in the epsilon environment of K. Right. Now I have to show that this is the limit of this guy. So I have to select the epsilon arbitrarily. Let epsilon be bigger than 0. Okay? Now let's have the half of the epsilon, my epsilon 1. You'll see soon why I need a half and not the whole thing. Okay? So, I have now epsilon 1. Now you can read this for an epsilon 1. It should hold for any epsilon, even for this one. Okay? If you don't like the names, you can switch the name. But it should hold for any number, really. You can call it any way you want it. For any number. So for this one too. So let epsilon 1 be alpha of this choice here. Okay? There must be according to the fact 1 and the fact 2, there must be, or there is, if you like, delta 1 and delta 2, so that both of these guys must be bigger than 0, so that f of x minus L is less than epsilon whenever x minus a is less than delta 1. How do I get that? I get it out to fact 1 here. Right? If you have this guy arbitrarily chosen, there must be delta 1, so whenever x is within delta 1 environment around A, the f of x must be within epsilon environment around L. So there must be such a delta 1. There also must be a delta 2, so whenever the x minus a, x is within delta 2 environment around A, then the g of x must be within epsilon environment around K. In this case, for my arbitrary epsilon. So in this case, I'm looking for this epsilon, epsilon 1. Right? This doesn't say you have to have a particular epsilon. You can take any epsilon you want. It says whenever epsilon is bigger than 0, whatever that is. So that whenever now is epsilon half. Okay? So this is what we have. So again, according to the fact 1, I can find the epsilon 1 so that this is going to happen because the number 1. And I can find the delta 2 this is going to happen. So whenever the x is within delta 2 around A, then the g of x will be with epsilon 1 environment around K. So again, this first part follows from number 1. The second part follows from number 2. Both of this says whatever the epsilon is, you can always find delta 1, so that this implies this. The second part says wherever the epsilon is, you can find the delta 2, so that this implies this. And that's what I'm using. And I'm not using, I started with arbitrary epsilon, and now I'm making a half of it. And so I know now that I must have a delta 1, so that whenever this is the case, this is going to happen, for this particular epsilon. And I can also find a delta 2, so that whenever this is, this must happen. Okay, now what I want to do. I want to do the following. And this is a tricky one. This guy. Minus this guy. You can first write with the parentheses. And then you can free the parentheses, write negative L, negative K. But this is what's gonna, let's write that. This is what's gonna happen. This is a trivial algebra. It's not an algebra that you would have a problem with. I hope so, right? So I have the f of x minus L, g of x minus k. But what we know about absolute numbers, absolute value of numbers, we know that when you have the absolute value of sum of two numbers is either the same or less than when you just sum them separately with the absolute. I mean, if you just take an absolute value before you sum them, and then you sum the absolute value, you will always get something that is either equal to what you do or bigger. This is a story I'm talking about. 2 plus 3. When you take an absolute value, is the same as if you take absolute value 2 plus absolute value 3. Because you are adding. Okay? If both are negative, you got the same thing. If you got negative 2 and negative 3, when you take an absolute value of the sum of negative 2 and negative 3, is the same as if you take the absolute value of negative 2 and negative 3 and then you sum. So whether you're going to sum them or take an absolute value makes no difference, they are the same. The only problem is when one of them is negative, one of them is positive, you get something else. So for example, you have negative 2 plus 3, so the first one is negative, and now it's not equal to negative 2 plus 3. When you separate and use the absolute value and then you sum, you get something different. This is 5, and this is of course 1, right? But it's no bigger, it's less. In this case, it's just straightforward less. And the same thing happens if the other one is negative. So if you got negative 3 and positive 2, again, you're going to get something small if you just take the absolute value first. And then you sum. So again, if you take the sum first and then you take the absolute value, you will never get anything bigger than if you take the absolute values first and then the sum. Okay? So, this is for 2 and 3, but you can argue with any number you like. What I'm saying here, that this is the fact of a simple algebra. If you do this, sum first, then absolute value, it will be less than the absolute value first and then sum. So again, you have 4 different possibilities. This could be positive, this could be negative, this could be negative, this could be positive, in which case this will be exactly less. And you could have this positive and this positive, in which case you have this equal, and this negative and this negative, in which again you have this equal. So it's this. In these 4 possibilities, 2 of them will end up with being equal here, and 2 of them will end up with being not equal but less. This side is always no more than this side. That's good enough. This is my A, this is my B. So it's no more than f of x minus L plus g of x minus k. Now I hope you can see all of that. Lots of stuff around. Beauty. Now what I know. Let's take a look here and take a look here. This one is less than epsilon 1, and this one here is less than epsilon 1. Now you can see the idea why I wanted the epsilon 1 to be the half of the original epsilon, because when you add it, I'm getting an epsilon there. I have a half of epsilon plus half of epsilon, which is an epsilon. And what we have shown, equal, less or equal, less, well, we have shown that f of x plus g of x minus L plus k, the absolute value of that is less than epsilon. And now you just have to pay attention to what we needed to show. We needed to show this. Whenever you have an epsilon, let's take any epsilon, you will find a delta. Ooh, what delta we have? We have 2 of them. We have 2 of them. Well, take a smaller one. Because if this is even closer than whatever this is, then this will hold. It says holds for anything in that environment. So if we make it smaller, it will still hold. So this is another one. So I don't know which one is bigger. So I'm just going to take a smaller one. Delta is smaller one. Minimum of delta 1 or delta 2, whichever is smaller. Okay? So again, take an arbitrary epsilon. Any epsilon. you can find a delta, smaller one of these two, so that this will happen. Whenever x minus a is less than delta. All right. Ooh, this is complicated. But I have what I wanted. So let's repeat this one more time. Take an arbitrary epsilon, whatever you like. You will find a delta. This delta I'm choosing here is going to be smaller one of delta 1 or delta 2. So whenever you have x minus a less than delta, what's going to happen is that x minus a is going to be less than delta 1, because it's not a bigger one. It's one of the smaller ones, right? One of them that is smaller. And this is also going to happen, which means that this is going to happen and this is going to happen, which means that this, and this will going to happen. Right? This is straightforward algebra, but from here to here, I'm using this fact of algebra. And from here to here, I'm using this and this. And finally, I'm adding these two, I'm getting what I needed, epsilon. So whenever I choose epsilon, whatever that is, I will find a delta, this delta. Yeah, I first need to find delta 1 and delta 2, blah, 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 but we have them, because they're guaranteed by 1 and 2, because I do have a limit here, and I do have a limit here, so there will be delta 1 and delta 2. Take a smaller one. And so whenever this happens, this and this will happen, which means this and this will happen, and then this follows. And that's the delta, epsilon delta definition of a limit. So whenever you choose an epsilon, you can find a delta. So whenever the x is in delta environment around the target of x, the function, the y, will be within the epsilon environment of its target limit, which is a plus k. So this holds. Okay? I want you to think about this. There's lots of implications this. The biggest problem with this is there are implications with lots of generalities in it. Okay? And I know the proof is difficult. So I don't even intend to go any further with the other properties proof, because they will go the same, well, not the same way, but they would use the same rigorous definition of what a limit is. But they all hold. They all can be proven by using that definition. What we are going to do in the future, actually, we're going to use those properties. So for now, I just proven 2 of them. But for now, you can start believing in them, and if you don't believe them, you can go in the textbook. They're in the appendices of the textbook, all of them proven, more or less. I mean, they might not be in the same number, and they might not be in the same section of the textbook, but you can find them, all of them, if you read the textbook. All of them hold. Okay? Now you can see that mathematical proof is not a cheap business. It involves something that you know, something like that. This holds for all of the numbers. I was not sure whether you know this or not. You're supposed to know that from algebra, but if you don't, you can verify. Again, in here you have 4 cases. A positive, B negative, A negative, B positive, A negative, B negative, A positive, B positive. In 2 of them, this is an equal thing. In 2 of the cases, it's going to be strictly smaller. And of course, you can have A or B equals 0, but then it's really nothing to prove, right? If A is equal to 0, you have a B, absolute value of B is less or equal than absolute value of B. That's peanuts, right? That of course holds. But I was assuming that you know that. Again, this number 1 and number 2 follows from premises. We call it assumptions, right? Premises, something that you assume to be true. So if this is true, then 1 must hold. If this is true, then 2 must hold. So I'm using that. Again, the delta is the one that depends on epsilon. So in the first fact here, the delta 1 is labeled delta 1. In the second fact, delta is labeled as delta 2. because I don't know if they are equal. This one depends on the function and on this epsilon. This one depends on this function and this epsilon. So, you know, a function can make a difference. So they could be different, but I need to be able to find them because I have the limit and I have the limits. So that's it. And then I start with an arbitrary epsilon. Now I'm using the half of that epsilon in here and in here. Because this says whenever epsilon is bigger than 0, not just you know, particular epsilon, any epsilon. So I'm using this epsilon now. Okay? And so again, there must be delta 1 and delta 2, so this is going to happen whenever this happens, that's a fact 1. And this is going to happen whenever this is going to happen, that's a fact 2. And then I'm using a little algebra again. So now I'm subtracting this minus this, because I need to prove that this is going to be in the epsilon environment of this guy. Whatever the epsilon is, as long as I can find the delta, so that the x is within the delta environment of A. So that's what I'm doing. So I'm saying, okay, what delta you need? Take a minimum of the two, smaller one. Okay? So, if you take a smaller one, this is also going to hold for any smaller delta here. Whenever the x is even closer to A, this is going to hold. Because it holds for all of them that are, you know, slightly further. It might be slightly further. Okay? So I'm splitting this by using this piece here. That's how I get here. And I'm saying this must be less than epsilon 1. This must be less than epsilon 2. Again, I'm using this. I already have that in this part. And then, of course, now you see why I needed the half of epsilon, original epsilon. I need the half because I want to have a conclusion about the epsilon. Okay. It's a difficult thinking here. You can congratulate yourself once you spend some time. You can rearrange this in a little bit different way than I did. But once you find all of the implication, all of the conditionals hold, and you understand why they are holding, you'll be very happy with yourself. Because I remember when I was a student like you in calculus, I spent some time on this, and I was thinking about it, and I went through every single one of those properties. I proved them all, and I have no questions about any one of them. But it took a long time for me to understand why the things work the way they work. All right. So this is the Friday intended lecture in a little more organized way than what I did when I was working on the live stream. All right. I want to keep this up for you so you can check it out.